The following is a public service announcement from the School of AI. Do you enjoy watching frags rack up in multiplayer video games but aren't very good at them? Are you not very good at video games but want to be able to post videos of epic boss fights to impress your friends? If so, then you may find immense satisfaction in having your very own AI which plays at a superhuman level and wins every single game in your name. Simply contact your local Move 37 course graduate who can help you build one. There are many chores in life, like mowing the lawn and taking out the garbage that we don't enjoy but have to do anyway. Finally, playing classic video games doesn't have to be one of them. If you're the kind of person who finds yourself forced to play tedious video games but doesn't enjoy it, there's finally a solution. Deep Q Learning is a breakthrough that can play video games for you so you can do better things like laugh at the latest cat memes on social media. Contact your local Move 37 graduate and ask for a Deep Q Learning bot to play your least favorite video games so you don't have to. And now, welcome back to the next coding tutorial, where we will take you deep into the world of Q Learning. Gone are the days of grid world and shallow Q. We're going to take you deep underground into the world of building AI which has mad gaming skills. And, in all seriousness, while automating the playing of video games may not have a huge impact on our lives, it is simply an analogy for real-life tasks like robotics, self-driving cars, and solving other complex real-life problems. If we can write code which masters complex video games, we can use that same code to master complex real-life problems. So last time we took a slight detour away from the Bellman equation to teach robots how to walk with augmented random search. You learned how to build a very rudimentary shallow neural network. Now, if you haven't heard the news, we are going to go deep. Previously, with vanilla Q-learning, we were storing a huge lookup table whose size was the number of possible states times the number of possible actions. Now with video games, even if we resize the screen down to 64 pixels by 64 pixels, we're still looking at a lookup table 64 to the power of 64 bytes. That's a number with 115 zeros at the end. It's not practical even for the world's most powerful supercomputers. And in addition, for games with on-screen movement, each state will consist of several frames to allow the network to estimate the direction and velocity of objects. So how do we take Q-learning deep? It's actually quite simple. The Bellman equation and temporal difference stay the same. We simply replace the Q lookup table with a neural network, which approximates a function for Q of state and action. Now remember how we used the most recent value calculation and a learning rate to update our Q table? Instead, we're going to use backpropagation and stochastic gradient descent to update the neural network which estimates our Q function. If you've got a solid understanding of the Bellman equation and actually work through the previous coding tutorials, it shouldn't be that difficult for you to graduate to start thinking with neural networks. As usual, I think the best way to understand this is to start with an oversimplified explanation and gradually fill in the details. So here's a very simplified version of how the algorithm works. First, we initialize our Q of SNA randomly. We interact with the environment to obtain a transition state, action, reward, state prime. We calculate the loss. Loss equals the Q of S and A minus the reward squared. If the episode has ended otherwise, loss equals the Q of S and A minus the reward plus gamma times the argmax action for Q S prime A prime. Step 4. Update Q of SNA using stochastic gradient descent minimizing the loss function. And step 5, repeat step 2 until converged. As you recall from the previous Q-learning tutorials, in order to reach an optimal policy, we need to balance exploration with exploitation. As before, we're going to continue using the epsilon greedy method, starting with an epsilon of 1.0, all random actions, and gradually taping down over a fixed number of game frames. What we are doing with stochastic gradient descent is very similar to supervised learning, but one of the primary requirements of SDG optimization is that our training data needs to be independent and identically distributed, IID. But as we move from state to state by taking actions, the data is heavily correlated and often there's very little changes between frames. In order to handle this, we're going to implement what's called a replay buffer. We're going to store a long fixed length list of SARS prime transitions and randomly sample from them to update the network. As new data comes in, the oldest data is kicked off. By randomly sampling from a long list, this breaks the correlation that comes from sampling values right next to each other and allows the model to converge. Let's take a look again at our loss function for when the episode is not over. Loss equals Q of SNA minus the reward plus gamma times the argmax of QS prime A prime. We're doing a lookup for QSNA and QS prime A prime in the same step. These values are often very similar and neural networks often have trouble differentiating them. Updating Q of SNA can mess up the QS prime A prime calculation and make training unstable. In order to avoid chasing our tail, we're going to use two separate copies of the same neural network. The network we use to calculate Q of SNA will be updated constantly. The network used to calculate QS prime A prime will be updated infrequently at a fixed interval. Anywhere between 1,000 and 10,000 steps works well, depending on the game. Do you recall the Markov property from my Bellman advanced video? The past doesn't matter, baby. In other words, the Bellman equation makes the assumption that all future state transitions depend only on the present and there's nothing hidden in the past. The problem is that in a video game which simulates real-world physics, the past does matter. So how do you know if a character that's suspended in midair is falling or jumping? How do you know if a projectile is headed toward or away from our character? A neural network is going to make poor decisions if it doesn't know things like that. The solution is to create a buffer, stack several recent frames together, and use that buffer as the observation at every state. Now let's take a look at the architecture for our neural network. How do we take a large number of pixels from a screen and pick out which objects are important to achieving results in a video game? Well, it turns out the same neural network technology used in cutting-edge image recognition is perfect for applying reinforcement learning to screen pixels. How this works exactly is beyond the scope of this tutorial, but I've linked an excellent explanation by Siraj in the description below. We're going to use 3 layers of convolutions, each one passed through a ReLU activation. Finally, we have a fully connected hidden layer, ReLU activation, and the output layer, which spits out the values of each action. Alright, now let's take a look at the final algorithm we're going to use. Number 1, we initialize the parameters for Q of SNA and our target Q network with random weights. Step 2, with probability epsilon, we select a random action A. Otherwise, we run the observation through our network and choose the action with the highest Q value. Step 3, execute action A in the game and observe reward R and the next state S prime. Step 4, store transition SARS prime in the replay buffer. Step 5, sample a random mini batch of transitions from the replay buffer. Step 6, for every transition in the buffer, calculate target Y equals R if the episode is over. Otherwise, Y equals R plus gamma times the highest Q value for state prime, action prime. Step 7, we calculate the loss equals the Q of state in action minus Y squared. Step 8, we update Q of SNA using stochastic gradient descent, minimizing the loss function. Step 9, every n steps we copy the weight from the main Q network to the target Q network. Step 10, we repeat from step 2 until everything is converged. For deep learning frameworks, TensorFlow and PyTorch are the big heavyweights. They're both excellent at getting any deep learning job done. TensorFlow has some excellent advanced features for deploying models into production at enterprise scale. It's also great for those who want to squeeze every last ounce of performance out of huge training jobs and production models. But it comes at the cost of a steeper learning curve. At School of AI, we want to make deep learning understandable to the widest possible audience, and PyTorch is definitely simpler and easier to learn for beginners. But if you prefer TensorFlow, you shouldn't have much trouble translating the code over once you know the basic principles. And if you already know TensorFlow, well, it shouldn't take you more than an hour to figure out how PyTorch works. Here we're starting with the simplest possible implementation of Q-learning. Make sure you fully understand it before moving on. Reinforcement learning started out with simple applications of the Bellman equation and then gradually involved enhancements and workarounds when that performed poorly on tasks. The basic implementation of Q-learning can only handle fairly simple tasks, so we're going to start out with the classic game that started them all, Pong. Then, as we study the DQN enhancements, we can try out more complex games like Doom and start the real fragfest. Alright, now onto the code. The first order of business will be to introduce the wrappers, which will help us prep the input data. Oops, wrong kind of wrappers. This is more like it. Skittles. Taste the rainbow learning. Rainbow learning is a real thing, and you will be learning about it soon. So in OpenAI Gym, wrappers are a layer of code that takes observations, raw pixels from the environment, and processes them before they go into our neural network. Wrappers can also take the actions we specify and transform them before they go into the environment. The wrappers are stacked and processed one after the other. The first order of business. Many Atari games require pressing the fire button at the beginning of an episode to start. The Fire Reset ENV wrapper does this for us automatically. Next up is frame skipping. Training will go much faster if we don't have to make a decision for every single frame of the game. With Atari, we can still play games very well by only processing every fourth frame. The max in frame skip environment wrapper skips through 4 frames, repeats the same action for each frame, and returns the observation which had the highest reward. Next, the post-process image wrapper is going to convert the images to black and white and downsize them in order to reduce the computing power required to process them. We convert to black and white, but weigh the red, green, and blue channels differently in order to get the best results. We resize the image, then crop it and output a NumPy matrix 84 pixels wide, 84 pixels high, with 1 channel, black and white. Each value is a byte from 0 to 255. Moving on, PyTorch requires tensors in the form of channel, width, height, but our data is currently in the form of width, height, channel. This simply moves the channel axis into the first dimension of the input tensor. We're almost to the finish line. Buffer wrapper tracks the last 4 frames and stacks them into a tensor. So we have 4 frames of different timestamps. 1 channel, 84 pixels wide, 84 pixels high, a tensor of 4 dimensions. The last step simply converts the black and white pixel values, which are bytes between 0 and 255, to a single float between 0 and 1. This is what goes into our convolutional network. Here we generate the stack of wrappers. Each time we reset the environment or step with an action, they execute from top to bottom. Think of a dream within a dream within a dream, just like the movie Inception. Alright, that's a wrap for our wrappers. Let's move on to the network architecture. Recall that our input is 4 frames with 1 channel of 84 by 84 pixel images. We have 3 layers of convolution. The first takes in all 4 frames and outputs 32 convolutions. The second takes in 32 convolutions and outputs 64. The last layer takes in 64 convolutions and outputs 64. The output of each layer is run through a ReLU activation, which cuts off all the negative values. There's a function to calculate the shape of the convolution output, which runs once when the network is initialized. It passes through dummy input data and measures the size of the output. Next, we have a hidden layer of 512 neurons followed by a ReLU activation and an output layer with a neuron for each action. The forward function runs the input through the convolution, flattens it to a simple array, the view operation, and runs it through the fully connected layers to get values for each action. Alright, now it's time to move on to the main training code. We'll start with the hyperparameters. Mean reward goal. When the average reward for the last 100 episodes exceeds this threshold, we've solved the task and training stops. Gamma, the discount factor for the Bellman equation. Batch size, how many transitions we randomly sample from the replay buffer each training step. Replay buffer size, the maximum capacity of the replay buffer. Replay min size, the minimum amount of transitions we need to accumulate in the buffer before we start back propagating the network. Learning rate, the learning rate used by the Atom optimizer. Sync target frames, how often we copy the main network weights over the target network, which is used to estimate the value of the next state in our Bellman calculations. Epsilon start, the starting value for epsilon, the probability of taking a random action. Epsilon final, the minimum value epsilon will reach. Epsilon decay frames, the number of frames epsilon will take to decay from the start value to the minimum. Let's look at the experience buffer. It simply stores a list of state, action, reward, done, next state, transition tuples. The capacity is taken from the replay buffer size hyperparameter. The sample function picks batch size transitions randomly from the buffer. It returns separate lists of the states, actions, rewards, Boolean dones, and next states. Moving on to the agent class. The only interesting function here is play step. This applies the epsilon greedy algorithm, either taking a random action or inputting the current state into the neural network to calculate the optimum action. The only complicated part of the code here is converting between NumPy and Torch and transferring the data to and from the GPU if you're using CUDA. We then feed the action to the environment and append the experience gained to the replay buffer. We also track the total reward for each episode and return the total reward only when the episode is complete, in which case we also reset the environment. Next comes a function which calculates the loss for backpropagation. It takes a batch randomly sampled from the replay buffer, the main network, and the target network. First, we convert all the input data into torch tensors and push them to the correct device. To understand this next line, you'll need to understand the input and output dimensions of the network. We pass in a list of batches of observations. Each item in the batch is a randomly selected game state. Out comes a batch of Q values for each action in the state. Actions V contains the actions actually taken. All we're interested in is the value of the actions we took, but we have a matrix with the values of all actions. The gather function takes a value of the index we specify along the axis we specify. The result of the operation is a list of the value of each action we took for each transition in the batch. Now we use the target network to estimate the values of state prime for each item in the batch. We run the list of next states through the network. This returns a list of the Q value of every possible action in the state. We take the maximum value from each row. Next, you'll recall the loss function is different if the episode is over. In that case, we don't care about the value of state prime. So we apply the list of true or false dones as a mask and set the next state value to 0 for every episode which was completed. If the done mask value is 0, not done, we use the value returned from the net. If it is 1, meaning the episode is complete, we set the value to 0. This allows us to calculate the loss correctly for all cases. If we forget to zero out the value of terminal states, the training will never converge. We don't want to do any backpropagation at all on the target network. This is updated every once in a while by copying the weights from the main network. So we detach the gradients to make sure they don't affect our predictions. Now, all that's left is to apply the Bellman equation. We multiply next state values by gamma and add the actual rewards received. The final loss function is simply the mean squared error of the difference between the actual values of states our network returned and the expected values. Moving on to the main loop. First, a few command line arguments. If you have an NVIDIA GPU, use the CUDA option. You can customize the name of the environment. You can also set the target reward. Training will automatically stop when the mean reward over the last 100 episodes exceeds this threshold. We make the environment and wrap it in our wrappers. We initialize the main network and target network. We initialize TensorBoard X, a tool borrowed from TensorFlow which allows us to visually track the progress of our training. Print out the network architecture once at the beginning. Initialize the experience replay buffer. Initialize the agent. Set epsilon to the start value. We're going to use the atom optimizer for gradient descent. Initialize things we want to keep track of during training. And we're in the main loop. We calculate the correct epsilon based on our decay preferences. And we play a single step of the game. If reward is none, then the episode is not over. I'm going to continue to the bottom of the loop and show you later how we handle a finished episode. First, we don't start back propagation until the replay buffer has reached the minimum size. Every certain number of frames, we update the weights of the target network by copying them directly from the main network. Here's the gradient descent operation. First, we zero out all the gradients stored in the network. If we don't do this, they will accumulate from the last update. Next, we sample a random batch of transitions from the replay buffer. We calculate the loss on the batch using the calc loss function from above. We update the gradients by backpropagating the calculated loss function. The Atom optimizer updates the weights and biases of our main network using the specified learning rate. And after all the training is finished, we have one thing left: close the TensorBoard writer. Now, real quick, back to the middle of the loop where we handle a finished episode. Most of this code simply tracks statistics, prints them out, and writes data to TensorBoard. We maintain a moving average of the reward over the last 100 episodes. If the mean reward has hit an all-time high, we save the model to disk. And if the mean reward is greater than our target, we break the loop to stop training. That's all there is to it. A link to the code is in the description below. I've included some tips in the GitHub README for installing the dependencies, but it should be fairly simple. You'll need Python 3 for this. Make sure your virtual environment is activated if you're using one. Just run dqn_basic.py and don't forget the --CUDA option if you have an NVIDIA GPU. To run TensorBoard to watch the training progress, just open up a new terminal with your Python environment activated. Type TensorBoard --logdir runs. You'll be able to watch the progress with several cool graphs. This took me about 2 hours to train on my NVIDIA GTX 1080. It would probably take about 4 to 6 hours to train on a modern CPU. It took us around 400,000 frames to reach an average reward of 17 and 1 million to hit our target of 19.5. All right, let's look at the results. Wow, that is one badass Pong bot. In the next episode, we're going to take this beyond Pong and rack up some epic frags in the classic game of Doom. You'll learn a few really cool enhancements which allow Q-learning to work on more difficult games. This has been Colin Scow, and I'll see you soon. Until then, happy coding!